I would like to thank the organizers for invitation. It's great to see you all. So I somehow have not realized until very recently that mine will be the first lecture in the series, but so I will try to give you a kind of a little gentle introduction. These lectures and actually some of the other lectures in schools will focus on the idea on building large-scale and useful quantum systems. And this is a part of the ongoing quest. Sometimes we call it a quest for controlling quantum world. And what we are trying to do here is to isolate and control some objects which in some ways simple, like single atoms, single ions, single superconducting qubits, and then try to use them as ingredient to build more and more complex systems from them. And the hope is that, as we kind of scale them up, as we build larger and larger systems, we can actually still maintain the exquisite control, basically fully control the quantum states, and then kind of that way build large quantum mechanical superposition states and try to use them to explore, for example, new physics. And typically this will be physics with this engineered many-body systems involving creating and probing new types of entangled states of matter. And we also would like to explore new applications. And of course, the subject of this school is mostly quantum simulation and quantum information processing. So this is now a very exciting field. And you hear almost daily in the news there is something happening. But it is, in these times, it is often kind of sobering to take a step back and reflect a little bit. And specifically, I think there are many outstanding questions in the field. So you guys have still some work to do. So, and two of them, maybe most important questions are the following. So one is how to build large-scale quantum systems. So at the moment, if we are really honest to ourselves, we do not know if and how truly large-scale systems containing millions of good qubits, which can make errors, less than 1 part per billion per operation. We don't know if this can be done. There are some good ideas, and you will see in these lectures and also in a conference next week. There is a good progress being made, but there are still many outstanding challenges. And the second, maybe even more staggering question is if I were to actually bring with me here a quantum computer and would give it to you, you guys are very sophisticated audience. You probably have some ideas, what to do with that. But in reality, actually, the number of these ideas is quite limited. So that's what sometimes we call it an application challenge. So, and basically, the question here is how we can use these systems to really achieve some useful quantum advantage. So, throughout my talk, I will be talking about both of these kind of topics. But kind of with this sort of gloomy or kind of critical introduction, I should immediately jump forward and say that it's actually a very special time in the field. There is a lot of progress is being made, and this progress is addressing what I sometimes call ultimate quantum rivalry. So this actually has to be understood kind of in very broad, kind of almost philosophical terms. So for example, competition between different platforms. This is not what I mean. What I mean is that basically building quantum system is like large-scale quantum systems is like kind of addressing two contradictory forces of nature. So one of this is this force of scalability. As I already said, what we would like to do is we would like to start with some elementary quantum objects like qubits, for example, and then control them with very high fidelity and build more and more complex systems and circuits out of them. And the second, and of course, what we'd like to do here is maintain the quantum state to be near pure. But then the second, is the scalability. What we need to do, we need to put a lot of these objects together And in basically almost any area of human activity, if you make the system larger, it becomes more difficult to control, right? So, for example, if you have a large organization with a number of smart people, like for example, PhD physicists and computer scientists, by definition, this organization will not be easy to control. So likewise, but actually in the quantum system, this is actually at the extreme. So basically, all of the kind of objects around us, like the tables or chairs where we're sitting, they consist fundamentally from quantum mechanical particles. But of course, once you put a large number of them together, they lose quantum character, right? And this is like kind of almost on the law of nature, which we take for granted. So in building quantum computer, we really have to win against this. We have to basically circumvent this law. That's the issue, and this actually is quite fundamental challenge. Okay, so the current frontier is that there are now several systems which can actually execute tasks which are beyond what classical computers can do. So if you, for example, have something order of 100 qubits and kind of sufficiently deep circuits, even representing the state classically exactly is it possible. These tasks are not necessarily useful, but that's something that hopefully will be addressed and in my lectures and also in the future. So, but these systems are super useful because by doing these experiments, we learn how to build bigger and better systems. And also we can now start exploring this kind of application for frontier. So we can start using the systems to drive some algorithms and kind of see, if we could actually find some promising directions. So in some way, I can kind of call it sometimes the age of quantum discovery, where basically you can use the systems to really start kind of explore and make kind of new discoveries. So by the way how I would like to kind of proceed with these lectures is that you can interrupt me at any time and ask questions, and I will also stop from time to time to see if there are questions. But if I don't hear any questions, I will ask you questions. So, any questions about this high level of introduction? There was not much information communicated, so maybe not so much. Okay, so I will now focus on the main subject of my lecture, and that is building quantum processors from cold neutral atoms. And this is one of the candidate systems, and some of you guys have seen the slides, but you've seen quite some of my lectures. So so the key advantages compared to other systems is that the neutral atoms have excellent continuous properties. So for example, so one of the most amazing devices that humankind has created is atomic clock. So atomic clock is probably the most precise measurement instrument ever created, and has an amazing coherence, right? It's now the stability 10 to the something, minus 20, right? So we would like to take advantage of this excellent coherence properties. So secondly, it's relatively easy to create a large number of atoms. In this room, there are a lot of atoms and molecules. So if we could control each of them individually, it would be a lot of qubits, And thirdly, I think also important in many applications, it's important that you can optically control these atoms and couple them to one. But also atoms have some challenges. So one is that, generally atoms, at least in the gas phase, interact very weakly. And also neutral atoms are hard to control individually, at least in large numbers, or at least that has been the case up until recently. So the kind of, to emphasize this challenge, so this is a picture of the atomic cloud. So this is how all of the cold atom experiments start. So they start with the cloud of atoms in the so-called magneto-optic trap, which are basically slowed down using laser cooling and trapping techniques. So basically what it means is that there's atoms and a gas phase, but they move very, very slowly. And so this picture contains, for example, 10 million of atoms, but if you want more, you can create more of them. They basically, what it means is that we have a source of cold, nearly identical atoms, which is essentially unlimited. And the key question is how to kind of build an efficient classical control techniques which would allow us to isolate these atoms, kind of arrange them, manipulate them, and use them as ingredients for quantum computing. So the way how this is done is using something which is called optical tweezer traps. And the idea is the following. So if you take a laser light and focus it very tightly, it will have the point of highest intensity. So at the focal point, and at this point, so the atom is a kind of, each atom and can be thought about as a kind of small dielectric object. So this object will have some polarizability. So, and this light will polarize this atom, and this atom then will be like a dipole attracted to the point of highest intensity. So, depending on how you arrange the tuning, this, often on the side of polarizability, this will be, attracted either to the largest intensity, or sometimes we can actually also push it opposite to the point where intensity is lowest. And using this type of approach, this atom can be actually basically trapped and held in the vacuum. So, the kind of overall approach to which I will be describing will start with an array of tweezer traps, and then we'll just load them. Stochastically, note that the depth of each of this trap, of this trapping potential, will not be huge. So it will be typically tens or maybe hundreds of megahertz, and just in terms of temperature, gigahertz is what? It's like 0.1 Kelvin, right? So what it really means is that these atoms should be actually cooled, to sub millikelvin temperatures, and this is done actually in our room temperature system in the vacuum using this kind of laser cooling techniques. So basically, a lot of this work is based on basically several decades of development of this techniques. Yes.
Could you explain what's
Okay, yeah. So this is it's taken from the course I'm teaching. So there are some people who took this course. So this mega delta is the radio frequency of the laser light, which is used for trapping, and delta is a detune from the resonance. So this thing is actually a very fundamental feature of kind of atom light interaction. So basically, this is in perturbation theory. It's what's called light shift. It's how much detuned light shifts effectively the energy level, right? So that's actually an alternative. Like you can think about either in terms of polarizabilities for trapping, or you can in terms of shifts of the levels. So that's I'm sorry about this. So it's eminently not defined here. So, any other questions? Yeah. Yeah, so let me explain this in a second. So, okay, there are different procedures. So kind of one of them is essentially the fold. So one is that you can start with this kind of, big blob of atoms, and essentially reject either a single tweezer or kind of more generally the entire array of tweezers. And so what happens in this case, is the following. So suppose you now focus these tweezers very tightly. So if you focus these tweezers very tightly, then what happens is that, the volume of the trap is so small that each trap can hold at most one atom. And the reason is the following. So if you have two atoms, and if they are closely spaced, then these atoms start to interact And actually either both of them or sometimes one of them get ejected from the trap. So it's basically kind of at a high level, your trap becomes so small that it can just host one atom at a time. And so in this way, what happens is that if you start with these atoms, which are very slowly moving and project these traps, then each of these traps, will either have an atom or not. So the loading process will be probabilistic, stochastic. And so what you see is that this system has a lot of entropy, classical entropy. So to get rid of the entropy, what one can do is one can use this effect similar to what sometimes people call Maxwell-Kieman. So you can basically take a picture of these atoms and figure out which of these traps are full and which are empty. And so once you sort of figure it out, then of course, what you can do, you can just, for example, kind of, reshuffle atoms around, or you can, for example, also sometimes remove the empty traps and then just move the rest of the atoms in any kind of desired configuration. So that way, you can actually assemble an array of the atoms with nearly perfect filling, with more than 99% occupancy, and basically position these atoms almost kind of arbitrarily in space. So you see it can be done in certainly very well 2 dimensions. Sometimes even 3 dimensions. People can put this atoms together. So the only kind of limitation here is that these straps, because these are optical tweezers, so you have like optical diffraction and so on. So these tweezers are typically separated by actually kind of micron or sometimes couple of micrometers in distance, right? Because optical resolution generally, but not always, prohibits from bringing atoms closer to the wavelength together. So at this point, these atoms are basically completely classical. So they are prepared very well, kind of defined positions and in kind of defined internal states, but they basically don't talk to each other, they don't interact. So to make them interact, what we're going to be doing, we're going to be changing the internal state and exciting them into the so-called Rydberg state. So in this Rydberg state, what happens is that the atom size effectively increases, and that causes these interactions. Yes. Imaging will. Yeah, it will generally project the atoms. So I mean, it will. So this imaging will first off, allow us to figure out if atom is there or not. But in most cases, but not in all cases, we can discuss it. It will also kind of make a projective measurement of the internal atomic state where we will call the qubits. But sometimes it can, in principle, it can be done without that, but it's much harder, and we can also discuss it later.
Okay, okay.
Any other questions?
Sorry.
So how is the imaging done? Is it some kind of magnetic resonance or?
No, so imaging is done optically. So you shine light. So this, like, remember I showed you this bright bulb of fluorescing atoms, So you can actually detect the presence or absence of atoms one at a time. And the way, and what you do, basically you shine near resonant light and see how the atom scatters it, all right? And that allows you to both detect, in this case, if the atom is present or not. It will also allow you to detect which state the atom is present, because you can excite the atoms in a state-dependent way. That's how that's the high level how it's done. So, I mean, there are some caveats here. So, often here, for example, when you do the imaging, you have to shine a light in a very specific way to make sure that this light does not hit the atom. But actually, in fact, instead, in most of the cases, you shine a light such that the atom is also cooled while you do the imaging. And this can be done by, for example, shining a light of certain detuning of certain color to actually.
Then immediately scattering in.
And then what you do, you measure the scattering exactly. And typically, of course, you cannot capture all photons, right? But what you will do, you will capture some photons. And what it means is you have to typically cycle this up a few times. You have to excite it a few times so that you can detect maybe 10 photons. Yeah.
Next one, why?
Is what?
Because I think like even resolution is about 1 micron.
Yeah.
Suppose I think that's probably not small enough to actually. So are you suggesting that you have the Rydberg interaction on during the loading phase?
No, when you do this loading and imaging, the atoms are not in a Rydberg state. But what happens is that basically is the following. So when you excite the atoms, you typically for example, you start with the kind of ground electronic state, typically an S state, for example, for rubidium, it's a 5s state, and you typically excite it to 5p state. So it's an excited state, but it's a relatively low lying state. And what happens is that when this is not a Rydberg state, but still, if your atom is in this is excited, the atoms start to talk to each other. They start to interact. And in particular, what happens is that so if you now have two atoms, and if you, for example, plot the kind of interaction potential between these two atoms as a function of the distance, so you have atom 1 and atom 2, and the distance between them. So what will happen is that, so basically so you have now two atoms. Initially, the state is, let's say, both of them are in the ground state, right? But if you start, for example, imaging the atoms, right, to detect, how many atoms you have on a given site. So what will happen is that you will actually excite the atom to this 5p state and it will decay. That's how you get this fluorescence, right? That's how you do it. So, but actually now, imagine you have a pair of atoms. So if you have a pair of atoms, then what will happen is that you will excite the state where maybe one atom is an S state and another atom is P state, or the other way around. So it will be like this. Right? So you have actually a pair of states here. So either one atom excited or another. And so what will happen is that now, due to basically dipole-dipole interaction, these two excited states will start talking to each other. And actually, it sort of will result into kind of molecular. This is like a molecular physics, 1.0, not even 1.01, 1.0.1. So, but basically, so you have a pair, you have two degenerate states initially, but they start interacting and they start basically due to the interaction, there's a splitting. And what you see is that due to this splitting, basically, you have now a potential, interaction potential between the atoms. And what happens, for example, we end up on this on this upper branch, then this potential is basically kind of repulsive. It will actually push the atoms away from each other. On the lower branch, this interaction, this potential is attractive, but then what happens is you actually start creating a molecule, and if you create kind of a molecule, it will also not be trapped. So basically what we see is that once you have these two atoms and once you excite them, there are a lot of mechanisms which actually force at least one atom to be ejected. Does it make sense? I forgot what's the questions. Is it clear? Okay, so there. Okay, yeah, go ahead. Yeah. Any other questions? So let me talk a little bit since I started now talking about the kind of interactions between atoms. So of course, the main player here in these lectures will be the interactions between Rydberg atoms. So this interaction is relatively weak. So for example, it's actually very hard to use it to make the logic gate with high fidelity for atoms which are sort of separated on the scale of the micron. So to kind of circumvent them, we use the Rydberg atoms. And for the Rydberg atoms, the key feature is that in the Rydberg atom, electron orbits far away from the nucleus. And if you remember your introductory quantum class, when for hydrogen atom, when n is large, the radius of the orbit, scales as n squared. And what it really means is that, for example, if you take n equals 100, then the kind of effective size of the orbit for this large n is a fraction of the micron theta. So it's actually really, ginormous compared to the normal kind of case when you are the atom in the ground state. So as a result, if you apply even a weak electric field, this orbit will be deformed, and the atom will become, highly polarized. So it means that there is a very high polarizability, and this, in particular, this implies that if you have two atoms now, let's say in the same state, for example, NS state, the van der Waals interaction between the atom will actually scale as an 11th power of the principal quantum number, and as a result, it becomes very large. So, for example, for n equals 100, the van der Waals interaction is 14 orders of magnitude larger than the interaction between the van der Waals interaction between the ground state atoms. So it's a very strong interaction, and one could really make a very good use of them. Does it make sense? All right, since you are asking me any questions, so here is a homework for you. So this kind of understanding where this 11th power comes from is actually a very good exercise. And so I encourage you guys, while you are enjoying your ice cream tonight, to try to derive it. This actually is so you can do it from a very kind of way, just knowing that the radius scale as a square of n, and just using kind of a dipole-dipole interaction, as a kind of ingredient, kind of build this 11th power. So it's actually will be a good refreshing. So, and this is important, as you will see. Okay, so with all of that, so the reason why we like these Rydberg states is because they have a very strong interaction as described. They also have a reasonably long coherence time. So, for example, this Rydberg kind of typical for n equals 50 to 100. The lifetime of the Rydberg state is typically a couple of 100 microseconds. So this, of course, short by some measure, but it's actually long by some other measure. So, and this combination is what allows us to actually use the Rydberg states for high fidelity, entanglement, and logic. And there are different ways how to use it. So one way, which I will be sort of focusing on in today's talk, is something which is called Rydberg Lattices. And the idea is, so suppose you have two atoms initially in a ground state, and you excite them resonantly into the specific Rydberg state with specific n. So if the atoms are far away, then what will happen is that atoms will just undergo independent radio oscillations. But if you start bringing them closer and closer, what will happen is that, eventually this strong interaction will take over. And what it means is that, if you bring the atoms sufficiently close, below certain distance, what will happen is that, any state which has more than single excitation will be shifted away from resonance. So, in other words, the excitation of the atoms, so you will be able to excite, one Rydberg atom, but no more. So the simultaneous excitation will be blocked at distances smaller than this characteristic distance RB, which is called blockade radius. And it turns out that this is the essence of a Rydberg blockade. So, and it turns out it's actually a very good mechanism to, very robust mechanism to entangle atoms and do quantum logic. And the reason is that this Rydberg blockade effectively makes the interaction digital. So if the atoms are far away, then it's like they are non-interacting. But if they are close, if they are, if they are closer than this Rydberg blockade radius, this interaction is basically almost infinite. So this kind of digital character of interaction, as you can see, will be very important, in particular if you sort of want to scale the systems in a kind of robust way. So this also allows us to circumvent, for example, effects which I talked about here. So if you sit, for example, on this, if you excite the state, there is a very strong force between the atoms. This force will also entangle both internal and kind of motional degree of freedom. It's also decoherent. So basically, there are many reasons why this Rydberg blockade is special. So, so altogether, putting this all together, the approach which we will be pursuing will involve the following. So we'll start with individual atoms, and initially they will, be kind of located at some random spots. But once we sort of image them, we figure out where they are, we will rearrange them in a certain way, and then once they rearrange, so we will start using internal degrees of freedom of atom, like Rydberg excitation, or sometimes we'll just change type of state. I will talk a little bit more about it in a second, to kind of excite them. And then basically afterwards, after this evolution, we'll make a projective measurement. We'll again image the atom now in a state dependent way, in such a way to figure out, basically what's the final state of the atom. So this is the entire kind of process of this kind of quantum computation or quantum simulation. And this is now a very exciting, I would say, exploding field. So a couple of hundred new experiments are being built. There are at least 8 companies which are trying to kind of commercialize this approach already. So here are some examples. So there are now different types of tweezers, arrays, which utilize kind of different types of atoms, different kind of modalities. You can also combine this tweezer array with something which is called optical lattices. It's another way to trap atoms, which are basically periodic potentials using interfering ways. And people start using molecules in these tweezers, and some of these tweezers become very exotic. So this is, for example, a picture of a 2-species array from Henry Vernian lab in Chicago. I think he gave a lecture last year at the school, and this is the array from Manuel Ender's lab. I think it's more than 5,000 trapped atoms, cesium atoms in this case. And this is a very exciting frontier because, using this platform, you can start addressing very different questions. You can think body dynamics, quantum computing. So I will talk a little bit about both of them, also quantum metrology, and it's very much complementary to the optical lattices. So as you see that there are people are now exploring kind of different types of atoms. You can ask why. So because in principle, you can pick any atom from periodic table and use it. So to the leading order, basically each atom can be used, but then there are details which sometimes make one atom or the other atom more preferred. So, for example, many of the experiments use this so-called alkali atom. These are hydrogen-like atoms. So basically, you just have one electron kind of orbiting like a, an open shell basically. And the reason to use them is because, these atoms have relatively simple level structure. So they're actually relatively easy to control. We have very well techniques to cool them, to trap them, manipulate, and lock, but sometimes it's actually might be interesting to explore atoms with more complicated internal level structure. So, for example, questions you ask here, can you cool the atoms while preserving the internal state? So some of that is kind of is possible using, for example, alkaline earth atoms like strontium or ytterbium. But moreover, even if you have picked the atom, you have a lot of possibilities, for example, to encode qubits, because the atoms have a lot of internal levels. And so, for example, like two obvious approaches would be either to internal encoding qubit bit in the superposition of ground state and one of the Rydberg states, but again, this is just one state, and in principle, many around. Or, as you will see, kind of for digital quantum computation, the best approach is to encode the qubit in some kind of long-lived state, like a hyperfine state. It would be electron spin, nuclear spin state. And in this state, the atom can live, for many seconds, and only if you want the atom to interact, you will carefully pick one of the state and actually excite it briefly to the Rydberg state. So that's, these are these kind of different encodings. So, does it make sense? Yes.
We all keep the arrangement. Make it
I will talk a little bit about it. Yes. So, two-dimensional is, I would say, kind of state of the art in the sense these are the systems which are best kind of controlled and easiest to scale. So, in principle, you can trap atoms in 3 dimensions, but it comes with some advantage because you can, of course, pack a lot of atoms, but there is also some disadvantages, and in particular, 2-dimensional systems are very easy in terms of like parallelism because you can address multiple atoms at once without kind of any crosstalk. For a 3rd dimension, you lose a little bit of this parallelism, but maybe I can elaborate on that when I show how this trapping is done. I will talk a little bit about, Yeah.
You were saying that the Rydberg blockade makes the interaction.
Yeah. Yes. So what I mean is this. So basically, typically if you have the normal, for example, interaction between 2 particles, right? As you bring them close together, like in this case, you have the interaction potential, which depends on separation, right? And so basically what it really means is that if, depending how they're positioned, you have different interaction strength. So for example, if you excite a state, get conditional phase, for example, this conditional phase will depend on separation, right? On exactly where atoms are located. But if you use this Rydberg blockade, this is different. And so it's different in a following way. So as I described, so if the atoms are sitting far away from each other, right, they are basically non-interacting. Okay, that's clear. But if we now bring them together, and if we don't try to excite this state, but still try to excite them resonantly. So in this case, basically, you will, as I already explained, you can excite this atom or this atom, but never both, right? And so basically, if you work with atoms which are either positioned far away or positioned well within blockade radius, so your interaction is either 0 or infinity to the leading one. Of course, there are corrections, and that's what makes it. And it's actually turns out to be very powerful. It greatly simplifies the control. That's the idea.
Gotcha. So the main idea is just that
it's either on or off.
Foods.
Yeah, it's almost like in a classical. It's either on or that's yeah.
Thank you.
Yeah. I will explain in a second. yes. I'll start. Yes. Yeah.
Say from this species, there's already some hot candidate crystallizing out, or is still, let's say, would you say, okay, still every species has advantages? For instance, we talk about blocks or about computation, that it's still worth to explore all of them. Or is there already some hot candidate way to say?
So the question is it really clear what's the best, basically, is there a clear winner among the different types of atoms? So I think the answer is probably not yet, and it's almost certainly the case that, for each given application, there will be, there will be a certain atom which will be, best. So, for example, it's very clear that for applications of metrology, we need something like alkaline Torf atom because you need a long-lived kind of optical superposition and optical transition, because that's what, basically it acquires the phase fastest. So that's what you want to use for clocks, But for example, for things like, quantum computing, for example, on atom like a strontium atom, there is still a research topic, but, it's really unclear if, for example, strontium is a good kind of qubit for quantum computing, because, for example, its optical transition is very weak, something which we take for granted with alkaline atoms, like, hyperfine, control with like exquisite precision, which is already, have like, close to 5 nines of fidelity, it will be very hard to achieve on this weak optical transition. So, and, then, of course, there are also Rydberg properties. So actually, for example, even within alkaline atoms, the kind of combination of what's called quantum defects, basically how the Rydberg levels, how the Rydberg atoms interact, the strength of the interaction is called C6 coefficient, in combination with kind of something which determines a short range properties, is a very important parameter, and it depends on combination things like quantum defects and so on. So it turns out, for example, for medium, they are much more favorable than for cesium, and the kind of the physics a little bit here is that this picture of this blockade, which I drew, is very good picture for atoms which are far away. So in reality, the way how, so basically, when the atoms are far away, you have this kind of very nice kind of blockade, interaction 1/6. But if the atoms come close, you basically have a lot of this kind of, overlapping, what's called spaghetti levels. So, and this actually is not, once you sort of find this regime, this is not a good approximation. So you would like to have a large parameter domain where you are under blockade, but not within the spaghetti, and for example, medium is much better than cesium. So basically, these are the kinds of considerations. So, so like if you want to kind of at the moment snapshot in time, medium is the best performing atom in kind of overall, for different considerations. For let's say quantum computing applications. For metrology, clearly strontium is the best, and maybe terbium is, I would say, the most intriguing because it has sort of some features which are, which are the combination of both. But it's active research. It's a very active research area. Yeah. All right. So let's start entangling at least, some others, here. So it was requested. So, the easiest way to create a Bell states with this Rydberg blockade is to pick the ground Rydberg encoding. It may be not the most robust way, and for various purposes, as I will describe, but it's the easiest way to illustrate. So basically, if you have the situation where you have a clean Rydberg blockade, where basically doubly excited state just is shifted very far away, then what you can do, and you can arrange it by bringing a pair of atoms together. So what you can do, you can basically just excite them resonantly. And so with these kind of conditions of blockade, you will be able to excite one atom or another, but never both. And if you create a condition such that you don't know which of these two atoms you excite, you will create an entanglement, you will create a belt state. So basically here, you simply just drive the atoms from both in the ground state to the singly excited manifold. And this phase now between these two atoms will be determined by the laser excitation phase. So, and you can basically verify that you create an entangled state by, for example, looking at the number of excitations. Here is the probability to have both of the atoms in the ground state. So here is the probability to have one atom in the Rydberg state, and here is two. What you see is that to excite two is basically not. This is the essence of the blockade, you know. And so if you now start these radio oscillations, it's at the point where you have exactly one atom here. So it's actually a belt state, and you can verify it, for example, by shining another light beam on one of these atoms to shift the resonance, to shift its energy level slightly, you know. And so what will happen in this case is that you will be able to couple these two belt states, which are, you know, which have a little bit different phase, you know, with each other. And that way you can actually kind of deconstruct, for example, a full density matrix. So that's how you can find that you actually have a belt state. So admittedly, this is not, this as you see is like already kind of, it's an old way to create belt states. So I'll show you there is a kind of a new way, which is actually much more scalable and so on, but already kind of here, you know, you can see you can have reasonably high fidelity, and actually in a recent work, this fidelity is actually much higher there, you know, starting to approach now 3 nines even, you know, and you know, the operation time is actually quite fast. In fact, you can do all of these gates in a kind of 100 microsecond, 100 nanosecond time scale. Does it make sense? Did I answer the question? Yeah.
What time should pay?
It's a laser, it's the distance and the laser. So you excite them with a laser going this way. So it's basically it's a combination of the distance of atoms and the phase between the two lasers. So actually, the way how you excite this atom to be actually precise, more precise, is with 2-photon transition. We use blue photon and then an infrared photon, and you know they counter propagate. It's basically K vectors is what defines it. Again, this will, you know, once we start doing, for example, hyperfine encoding. So here this phase is, you know, defined, you know, in a different encoding, it's sort of irrelevant because it can solve something. So does it make sense? Okay, that's the simplest possible example. But now, of course, with all of these ingredients, you can start putting them together in different ways. And like in this first lecture, I guess I have just, you know, maybe 10 minutes left or so. So I will just kind of explain briefly one kind of modality. And this is kind of an analog modality in which one could implement a programmable quantum simulator. So, and kind of the idea here is, so let's now go from 2 atoms to, for example, a chain of atoms in 1 dimension. And let's, for simplicity, space them with equal distance away from each other. And let's try to basically excite them into Rydberg state. So here again, we will use encoding involving ground and a Rydberg state. And basically in this this system, one can describe by the Hamiltonian, which will be an effective spin Hamiltonian. So kind of, and this Hamiltonian will have the following terms. So first, you know, if you drive it, you know, the rabbit term will be just, you know, coupling to the sigma x operator, you know, bringing atoms from ground state to the Rydberg state. So the second term is also a single atom term. It's proportional to laser detuning. So it's technically proportional to sigma z, but actually here we will write it a little bit different. So n will be a number of Rydberg atoms in each given lattice site. So it's like a sigma z term. Written in this way, it looks like a chemical potential. And then finally will be this interaction term. This is just a Rydberg interaction, which will, for example, create a Rydberg blockade. So it's actually this model is a kind of Eisen type model, and it has been analyzed actually way before these experiments have been started. And actually, it turns out that this simple model has actually quite interesting phase diagram. So this phase diagram can be specified by the detuning, this ratio of delta over omega. And the second parameter is something which we'll call interaction range. So basically, how many nearest neighbors for a given atom are at the blockade. And so, for example, what one could ask is one could ask a question. So, what is the ground state of this model? In the case when there are no interactions, the answer is actually very simple. So it depends on the sign of this detuning. So if detuning is negative, you want to have n equals 0. You don't want to have any Rydberg atoms. So that's the case here. So if the detuning is positive, you would like to have the opposite situation. You'd like to have all atoms be excited in a Rydberg state. But now, if we turn on the interaction, then what will happen is that this kind of state does not respect the Rydberg blockade, right? So clearly, even if just nearest neighbor at the blockade, I will not be able to excite all of these atoms in the state. So if only nearest neighbor under blockade, so a very natural state that we will be able to excite is a state where every other atom is in a Rydberg state, right? So this kind of state clearly, has some order, so it actually breaks to symmetry. So if you now extend the range of blockade even more, you will actually you will block not just nearest neighbor, but you block second nearest neighbor. So this state has a Z-free order, and basically, there is a kind of a full kind of hierarchy of the states like this, And this type of physics is actually very easy to probe. And so the way how you can do it, you can start with all atoms in the ground state and negative detuning that will be effectively the ground state of your system. And then what you can do, you can try to basically slowly change this detuning from negative to positive, try to enter into this ordered states. And this is exactly what you can do. And immediately you see how this order emerges. So basically, here are the images of all atoms in the ground state. So after you kind of go into the state with positive detuning, basically every other atom becomes excited. So you basically see that every other atom now is in the ground state. And actually, if you stop in the midway from this detuning, what you see, there is a lot of fluctuations. So this is actually a flat quantum fluctuation, which derives the so-called quantum phase transition. So if you bring the atoms closer, then not just nearest neighbor, but second nearest neighbor. Okay, so you get states like this. So up, down, down, up, down, down. So this goes on. And so basically, what you see here is just by arranging atoms, by changing their distance. You can actually sort of enter into different kind of ordered states, and actually it turns out all of these transitions are quantum phase transitions, are of different kind because they break different symmetry, and this actually you can really kind of regulate explore. So the kind of this is this one-dimensional system. So as I already mentioned, the kind of
What's the phase in the black region between the ordered phases?
In between. So it's kind of it can be in. So sometimes you can have just direct phase transitions between this, but sometimes when these phases compete, this can give rise to new types of phases, and sometimes this phase charges is the first order or sometimes second order. So it's actually kind of an interesting. So in particular, these are kind of chiral phases we actually explored it. It's been some time ago. So yeah, so but we can look up, some of the papers, and we actually, for example, there are sometimes you can have the tri-critical point. So it's an interesting, and actually some of this physics is kind of also related to like mesons and actually something in Alexei Kroshkov group started. So but yeah, so this is actually interesting. There are some interesting, things, but they actually become even more interesting 2 dimensions. So 2 dimensions for more recent, sort of remember better. But there is an interplay. You are completely right. Yeah.
Are there like interesting universal behaviors among?
Yeah, totally. There are. So in fact, I will explain in a second, how we can actually, probe, for example, critical exponents. So the way how we do it by changing the speed with which we change with the tuning. So we can look basically how many excitations you create. And we can explore things like, for example, Kibble-Zurich mechanism. And from this Kibble-Zurich, you can actually extract universal critical exponents. And we measured, not in this paper, but I think we had a 2018 and 2019, like a Nature paper, where we actually explored these different, exponents and measure them. And actually some stuff in between is kind of also that's kind of interesting. So totally one can explore universal and map these universal exponents. Yes, I will show in a second how this is done. Yeah. All right. So yeah, 5 minutes. Okay, good. Okay. So yes. So all right. So let me just kind of, I promised you that I will explain how these experiments are done in 2 dimensions. So it's kind of a state of the art in terms of control. And the way how it's done is one uses its device, which is actually quite an amazing device called spatial light modulator. It's basically a computer-generated hologram. So by just defining the phase profile, one can control the deflection of the laser beam. So it's actually this projector here works using very similar kind of principle, using a very similar device. And so with that, you can, for example, create a 2-dimensional pattern of traps with almost arbitrary configuration. And so basically when you project it in the vacuum chamber where there are these atoms, you can basically, have this, arrays of thousands of light spots, where you can grab the atoms. So this SLM is actually quite amazing, as I already said. So it has just one drawback. So it's actually relatively slow. So if you want to, for example, move atoms around, which already was important in the previous kind of when I talked about the arrangement atom, and will be more important in my second lecture. So this thing is not fast enough. So basically to move atoms around, what we do is we use this device called acousto-optic deflector. So this is actually a device where basically you put in a light beam and we use sound waves to actually deflect it. So it's actually the devices which are used, for example, for barcode scanners in supermarkets sometimes. But actually it's a relatively old technology, but actually it turns out to be super useful. And so basically, if you take 2 of these devices, you can then move rows and columns of atoms independently. And this is what we use to actually kind of move atoms around. It's all computer control. So basically you can rearrange the atoms. And so basically that way, for example, you can now, create, arrays into these. And so this actually, again, this is an old image from a few years ago. It's now much faster, but I mean, it gives you an impression. So you start now here with 600 atoms and you rearrange them 200, 300 atoms. So with high field. And so, and with this way, what you can do, you can now, basically arrange atoms in any different kind of configurations. And of course, like in terms of many body physics, in terms of programmable simulators, it immediately defines your geometry, how the atoms interact with each other. And so, for example, here what one can also do, one can create an arbitrary pattern. So these are the pattern what you want, you define it, on your computer, and then you just, press a button, and actually here the atoms are trapped exactly in these positions. And so basically, kind of with this kind of approach, one, actually state of the art is more like, maybe have create arrays with over 500 atoms, and each of these trap is filled with probability close to 3 nines. So basically, kind of going back to this quantum simulations, what one can now do, one can explore similar effects to what I just described, but actually now in 2 dimensions. And the simplest possible arrangement here is if you have, for example, square lattice, and if only nearest neighbors are blockaded. So if you then do the same, the same thing what I described before, you start with negative detuning, and then you basically, slowly change the tuning from negative to positive. Then you will end up with this arrangement where every other atom is excited in a Rydberg state. So basically, what you see is that this is like an ideal antiferromagnetic kind of pattern ordered state. And you can then start asking the questions how so it's 2 minutes. So it just will be a very logical place. So can you study this? This perfectly arranged pattern does not occur on every shot of experiment, so you can actually have to repeat this experiment many times and you can, for example, look at some correlation function. So this is actually this antiferromagnetic up down correlation function. You can also start asking microscopic questions. So you can ask how often does this perfect pattern appears, and actually it doesn't occur very often. In fact, the probability to find perfect arrangements decreases exponentially, but still by far most this pattern and the pattern where it is shifted by just one lattice site is by far the most frequent. So, and then you can also start asking questions about dynamics. So for example, what if you start going across this phase transition with different speed? So what you can do, you can, for example, extract from this type of correlation function, correlation length, and what you see is that depending on how slowly you go, the correlation length grows to a certain size, and actually this is where you can start exploring these ideas of universality. So, for example, if you take this correlation length and the detuning and rescale it appropriately, so you see that this curve collapses, and this is what allows you to extract, for example, the so-called critical exponents, and they universal for the given class of a transition. So, and this is, for example, like the critical exponents are characteristic of the so-called 2+1 Ising quantum phase transition, and this already is a work which is a couple of years old. But it's still it is still an active frontier. So, for example, I think Sophie Lee is one of my students. We are checking. I think she'll give a poster in this meeting. So, in fact, very recently we kind of revisited this, and it turns out that the correlations can grow not only due to the Skibble-Zurich mechanism, but due to other effects, something which is called coarsening. And this coarsening dynamics is also universal. And it has some very interesting features. It also, for example, one can observe the so-called Higgs modes, and this is actually will be, it's a subject of ongoing research. So, but again, so here we just started with the simplest possible arrangement of atoms. So one can actually now make things more complicated. For example, by going to larger blockade radius, or start with systems which are, for example, frustrated or disordered, and all of these things, can give rise to some very new kind of physical phenomena, and it's actually which one can be explored on the system. So, moreover, so far I've only talked about kind of ground state physics. The most exciting use of these quantum simulators is to push systems away from equilibrium. In fact, in this way, we actually made some discovery. This is the system where we observed for the first time with many body scars. And we're continuing kind of their exploration. Actually, some of these are all analog kind of simulators, and actually this analog system, similar to what one I described, is now have been available for last 1.5 years on the cloud through our startup company, Quora Computing. These are all the things, that are still very exciting direction, and it's still a frontier of information. So maybe it's a good point to stop the first lecture. Yeah. Thank you.
We have another question. Can you take maybe one or two quick questions?
This is a really good question. So I think you mentioned as slow in terms of speech increasers. So is there like a reason why you use DMD in this case?
Yeah, so DMD also has some limitations in terms of speed. So, you would like, okay, the question whether DMDs can be used is still maybe a subject of ongoing research. So the real question is, the speed, and also how does, if you want to dynamically kind of change your image, whether this can be done smoothly or it can be done kind of steps. And so this DMD is potentially could be useful, but it's not yet fully clear. Yeah, but certainly kind of, it's one example of using holograms. So we need holograms, and we need to continuously change them, right? And change relatively quickly on the scale, ideally, maybe tens of microseconds, so and I think there is a need, particularly as we scale up the system, and I will talk a little bit, to really think about new ways to generate these holograms. Yeah.
Thanks.